Again, welcome to today is March 25th. Today is, I think we're still finishing chapter 25. Okay. And we did some problems from chapter 25. We need to finish them. So let me go a little bit with what we did so far. I think we did problem 71. So I know a lot of you are not here today. So we're going to record this session. And hopefully you guys can look at these problems later on and do them. There was a question from somebody else in another class, so I really want you guys to remember this because it's very important. Can we have review problems for the exam? Okay. Well, I'll tell you this much, that the problems that we're doing in the homework and the problems that we're doing in the classroom are the bulk of the exam review. So you really need to do these problems while I am doing them or immediately after I do them. You really have to understand how to work these problems. If you don't know how to do these problems, you're going to have difficulty with the exam. So because they're actually preparing yourself for the exam. So again, chapter 25, we covered all the content for it last time when we met. And today we're going to basically finish the ideas for that chapter. And then after that, we're going to basically start chapter 26. So last time we did problem 71 when we finished the chapter. So let me go into my notes first of all. OneNote. And let me share the screen. Share. Okay. So basically we're doing problems from chapter 27. As I said before, we did problem 71. We're going to do problem 70. Then we're probably going to also cover problem 69. And that's to some extent, I already talked about problem 59. If not, I will give you an idea how to do those problems. We're not going to do all of these problems in detail, with the exception probably of problem 70. So we already did problem 71. So let's talk about problem 70. So for problem 70, basically what they give you in this case is they give you a battery. And the battery has a representation usually by this epsilon. The epsilon stands in here for EMF, the electromotive force. In other words, the voltage on the battery. I mean, if you have a battery, I'm trying to see, I have one in that bag. So if you, there, the battery has a number appended to it. This battery, if it's not appended, we know that this is a 1.5 volt battery. So that would be its EMF, okay? So the EMF on this battery is 1.5 volt. So that would be your epsilon. So when you're doing problems like this one, that is basically in a nutshell what you have to remember. So, and then you have a resistor R1. Typically in these problems, we need the switch somewhere to trigger the circuit. We want to be in control of it. We don't want the current to start right away. We have lab this afternoon and we will have switches in it to do the lab, okay? So if we are doing this live, you will see that usually the power supply has a switch. So there is another R2 in here, and there are two capacitors, C1 and C2. In parallel with this resistor. All of this are in parallel. The reason why I'm saying this in parallel, of course, I'm going to close the circuit in here. If I start numbering, if I number this one 1, and if I number this 1.2, this is actually the same point in here too, which is actually the same point in here too. So all of this are the same connection. There is no device between anywhere in here, between these points. So it's the same point. As a matter of fact, if I call this 1.3, it's the same thing as this 1.3, the same thing as point this 1.3, which is actually the same points as in here. All of them are identical, okay? So this is basically in a nutshell when we're labeling things so that you know. Therefore, since this capacitor C1 and this capacitor C2 are sitting between the same 2 points in the voltage, this has a V23 voltage, that too has a V23 voltage, that too has a V23 voltage. Same voltage means it's parallel. Because the voltage is the same, these things are parallel. Parallel. Okay. I can't say much about R1 with any of the other devices at this point because it's not necessarily in parallel or in series. So I'm going to leave it as that, okay? And they gave us values in here. First of all, the EMF is 72 volts. So this number is 72 volts. They also gave us the values of R1, I'm sorry, R2 being 2 ohms. So there is a 2 ohm in here. And they also gave us a capacitance C1 to be 3 microfarads. So this is a 3 microfarads. And they also gave us C2 being 6 microfarads, twice as much, okay? Okay, no problem, no problem, as long as you're here. Anyway, so this is the information they gave us. As far as the circuit, we don't know what R1 is. They didn't say that. They didn't say anything about R1. Actually, they tell you that after the capacitors have attained their final charges, that's why we really need the switch there to turn it on and wait and wait and wait. We probably need an ammeter also somewhere and a voltmeter to keep tab of this thing in here and wait until they're fully charged. At that point, there should be no current flying through any of this side. So if when it's fully charged, that means the current that is going to this capacitor is 0, and the current that is going to this capacitor is 0. So that means that this current in here that is coming, which is 0 plus 0, must be 0 also. So there is no current in here, which means that this current that leaves the battery, which I'm going to call I, since it cannot go through this junction because they're already fully charged, and the current serves to charge capacitors, that's all, then the current must be going through this resistor, and then coming back in here. So it cannot go through this side because they're fully charged also. It cannot extract charges from the other side. They tell you that when it's fully charged, there is a charge Q1 of Q18 microcoulomb in here. So there is a positive 18 microcoulomb in here and a negative 18 microcoulomb in here. That is what's going on in this situation. So we know that. And what is the final charge on capacitor 2? Since we know the charge on capacitor C1, and we know what C1 is, I know what the voltage between 2 and 3 is. So V23 must be the charge on capacitor 2 divided by, I'm sorry, capacitor 1, because they give us the value for 1, yes. Q1 divided by C1. Q1, they tell us specifically after the dust settles and it's fully charged, it's an 18 microcoulomb. C1, they tell us specifically it's 3 microfarads. For those who came in late, we're doing these problems, okay? We did already 71, so we're talking about problem 70 from chapter 15, okay? So now, all we have to do is find this voltage. So this voltage kind of cancel the micro, and 18 divided by 3 is 6 coulomb per farad, which is just a volt. So the voltage between here and here is 6 volts. But this point is the same as this one, and this one is the same as that one. So this must be also 6 volt difference, drop in potential. And between 2 and 3 also is a 6 volt too of a drop in voltage. So this entire voltage, because they are in parallel, must be the same voltage across each and every one of those devices, okay? So we found the voltage, but they didn't ask us to find the voltage. They wanted us to find the charge that is sitting on Q2, negative Q2 in here. That's what they want. Well, we know that V23 also is equal to Q2 over C2. And we just figured it out what V23 is. So from here, I'm going to find that Q2 must be C2 times the same voltage of 6 volts. So this C2, they tell us it's 6 microfarads. So it's 6 microfarads times the voltage that I just measured, which is 6 volts, the micro stays by itself. The farad times volt, that is actually coulomb. So 6 times 6 is 36, 36 microcoulomb. And that is the answer to the question. They want, I'm sorry, not Q2. They want the charge on capacitor 2. So the charge on capacitor 2 must be 36 microcoulomb. Because if I divide 36 by 6 microfarads, I will also find the 6 volt because they are parallel. Now that is question 1. Question 2. Now they want to know what this resistance is. They didn't give us that, now they want it. So we need to find what R1 is. So here is the deal. I need to know what this current is going through it. Once I know that, then I am going to apply Ohm's law and I'm in business. So let's do that. I need to find this current, and this current is the same current going through this resistor. So if I know the voltage drop in here between 1 and 2, then I'm in business. And I know that voltage drop. This is 72 between 1 and 3. So V1 and 3, which is, by the way, V1 minus V2 plus V2 minus V3, is 72 volts. Whereas V2 minus V3, I already figured it out to being 6 volts. So V1 minus V2 is 72 volts minus 6 volts, which is 66 volts. So the drop between 1 and 2 is 66 volts. If I figure out what this current is, then all I have to do is divide 62 volts by this one, because I know that V between 1 and 2 must be equal to Ri, R1I. Since if I can figure out what this current is, then all I have to do is divide it, divide it by the voltage, and I'm in business using Ohm's law. I can find what that R1 is. So let's find that current. Okay, we know from this expression in here that this is also 6 volt. And that current must be traveling through this resistor too, because it has to go somewhere. Because these are fully charged, it cannot go through them. So the only way for the current to go is through this R2. And comes back and closes the circuit when it goes to the battery. Now I have a current I flying through this entire portion of the circuit. Okay, so let's do that. This branch is forbidden when the two capacitors are charged. So the only branch for the current when it hits R1 is to go through R2. So, but I know what the voltage drop between 2 and 3 is. So again, one more time, V23 is, which is 6 volts, by the way, is also equal to R2 times I. That means that I must be equal to 6 volts divided by R2. And R2 is 2 ohms. So this is 2 ohms. So that means it's 6 volts divided by 2 ohms, and the answer is 3 amps. A volt over an ohm is an ampere. So the current must be 3 amps that is flying through this entire circuit. So there is a 3 amp that comes in here. Nothing can go to these fully charged capacitors. So the entire 3 amp need to go here. And that would give me that 6 volts, a drop in potential, because these points are the same, whether I calculated 18 divided by 3, which is 6 volt, or 36 divided by 6, which is 6 volts, or now 2 times 3, which is 6 volts. So all of the calculation give me the same voltage because they are in parallel. So the last thing in here, since I know what this current is to go back to this expression basically that I was writing and say the following. The voltage drop between 1 and 3, I wrote that one, so I'm going to write it one more time just to see it, minus V2 plus V2 minus V3. This is V12, and this is V23. This I calculated it to be 6 volt. This I know from this side to be 72 volts because this is the battery. So on one side it's 72 volts. And on the other side it's the sum of the other two. So this one is actually R1I. So what I have in here is 72 is equal to R1I plus 6 volts. So this is in volt, by the way. So that gives me the value of R1 being 72 minus 6 divided by the current, and the current is 3 amps. So this is 66 divided by 3, and the answer for R1 is, again, this is in volt, This is in amps, and the answer is going to be in ohms. So it's 22 ohms. Okay. So this is basically, in a nutshell, how this problem works. So let's summarize this. Think about this one, what they gave us. They gave us the EMF of the battery, 72 volt. They gave us the resistor R2 being 2 ohms. They gave us a capacitance in here being 3 microfarads. They gave us also the other capacitors being twice as much, 6 microfarads. And they tell us we charge basically the capacitors. And after they're fully charged, in which case they don't take any more charges at all. So that means there is no current in here trying to build up more charges on them. That means there is no current going through to this capacitor, and there is no more current trying to build up more charges because they are fully charged. So that means these two currents are zero. So all the current that is flying is actually has to go through R2. They tell us they know the charge. It's 18 microcoulomb in here on this capacitor. So that is a trick for me to find this voltage, because 18 divided by this 3 gives me a drop of potential between this point and this point of 6 volts. And that is the same voltage drop in here, and that is the same voltage drop in here. I know the overall drop, which is just that of the battery. That's 72 volts. But now I know more. I know this drop, which is this one, which is this one, because they are all in parallel. Now, they ask me to find what this charge is, Q2 is. Well, since I know the voltage drop between this point and this point is 6 volts, and I know the capacitance, all I have to do is multiply C times V, and now I'm in business. C is actually 6 microfarads, and V was 6 volts, which I found. So that's given me 36 microcoulombs, I'm sorry, for the charge in here. So there must be a negative 36 microcoulombs on the other side. Now they want to find this resistor. For that, I really need the current, because I can find the algebra in here to find what this voltage drop is. Turns out to be 66, because there is a 6 in here, and in here 72. 72 must be equal to this 6 plus something. And that something better be 66, because 66 plus 6 is the voltage drop across the capacitor, across the battery, which is 72 volt. Now we're in business if we find that current, because all I have to do is apply Ohm's law in this case, which is R1 times I must be that 66. How do I find that current? From this condition again, since they are in parallel. This drop is 6 volt. This resistor is 2. 2 times something must be 6 volt. And that something better be 3. 3 times 2 is indeed 6 volts. So the current must be 3 amps. And this current must be going in here too, because when this current leaves the battery, it's going to hit this junction. Part of it needs to go through here and the other part in here. But these guys are fully charged. They don't accept any more charges. So all of it has to go through here. So the 3 amps that is in here actually is in here too. Now I have 3 amps times this R1 must be equal to the voltage drop, which is 66. That means this resistor better be 22 ohms. 22 times 3 is indeed 66 volts. Does this problem make sense to you guys?
Yes. Yes.
Okay, very good. Okay, as I was saying before, the review for the exam, which is immediately after the spring break, is going to be these problems that we're doing together, including also the homework problems, okay? So that is basically in a nutshell what we're saying in here. Okay, so let's continue. I promised also problem 69. Problem 69 has an interesting idea in it. Otherwise, it really looks similar to this one. So let me go into share screen again. And we're still dealing with these problems in here. Anyway. Okay. So problem 69. Problem 69 has this interesting idea, okay? So in other words, we use this kind of ideas to find the salinity of water, how much salt does it contain in it? Because the more salt it has, and salt is an ionic structure, that means it's conductive. It conducts electricity. And I mean by its salinity in this case is pure NaCl, but it could be any salt actually. All salts have these properties too. They are good conductors because of their ionic structure, similar to regular table salt. Now, pure water does not conduct electricity because it has very weak conductivity. Okay, so that is basically in a nutshell what's going on. So let's do that. Let's look at the. You have 2 cans in here. The bases are conductive. So this is made out of metal. This one also is made out of metal. But the sides in here are not metallic. They are actually insulating. And the container in here is pure water. So on the other side in here, I have another can in here, similar size. Actually, they tell me specifically it has the same size, so I'm drawing it probably not exactly the same size. Okay, and they have an ammeter in here to measure the current. And we have a battery. And we have a resistor R. Okay, so this is basically in a nutshell. The geometry here is identical. This is a length L. This is the same length L, basically, and the base in here has a radius R, little r, not to confuse it with the big R in here, which is the resistor, okay? Two cylindrical cans with insulating sides and conducting end caps are filled with water attached to the circuitry shown and used to determine salinity levels. The cans are identical with radius R equal to 5 centimeters. So the radius R is 5 centimeters. And the length L is equal to 3 centimeters. Okay. I have 3 sig figs in here, so if I'm doing calculations, I have to be mindful of that. And the battery's EMF is equal to 10 volt. Okay. And which has a negligible internal resistance, because if it does have internal resistance, we're just going to add it in series with it, and that's it. Okay. Most of the time, we're dealing with ideal batteries. Practical batteries have internal resistance. Now they tell you R is 15 ohms. So this R in here is actually 15 ohms. Okay. The left cylinder is filled with pure distilled water, which has infinite resistivity. So basically, this is just a dielectric in this case, because it does not conduct electricity. So charges, when they're coming from the battery in here, they're just going to pile up in here, and the others are extracted from the other one. So this acts as a capacitor. That's it. Now I have to calculate the capacitance of that capacitor, which is epsilon naught times the area divided by the length. However, this is not air. This is not vacuum. So I have to multiply it by the relative permittivity of water. And they tell me the relative permittivity of the water in here in the back is 80.4. So epsilon R is 80.4. I think the book uses the letter K, but there's so many Ks in here. I use actually epsilon R, which stands for the relative relative permittivity. So epsilon R and K are the same, and this is the relative permittivity. Okay. That depends on the medium. For air and vacuum, it's 1. Except that we know that this is not the case. Okay? This is water, pure water. So they tell us that we needed that value, otherwise we cannot really calculate the capacitance. Okay. They tell you also that it is known, based on other evidence, based on experiments, that the resistivity of this material, now because we have salt now, so this is ionized, so this acts as a resistor now. So this acts as a resistance, which is equal to rho times L over A. So I need this rho now, and rho for water with this salinity, they tell you it's equal to a constant S naught over S, where S is actually the concentration of salt. And S naught is a nominal value in here that is only typical of water. Okay, for water, this is 63.30 ppt, parts per thousand. Basically, if the concentration of the salt increases, then the conductivity increases because rho decreases. So if S goes up, rho go down, which means that this becomes more and more conductive. Okay? If the concentration go down, if the salt go down, then in this case, it's going to be purer and purer, which means that the resistivity increases. So it's going to be infinitely resistive. It becomes more like a capacitor again. So this is the big idea from this this thing. So in other words, this resistance now I can calculate it. This R, I can find it now as being S naught over S times L over A, and A is equal to pi R squared. Since they gave me R, I can find A for both geometries. So I can find the capacitance and also the resistance. And they gave me L, so which is 3 centimeters. And I know epsilon R, which is 80.4. And I know permittivity in epsilon naught, which is 10 to the negative 12 times some numbers in that. Okay, so times 8 something times 10 to the negative 12. Anyway, so we have all the info that we need to do, with the exception we don't know what S is. We don't know what S is. So we really don't know what R is. So this is a question mark in here. We don't know what that R is because we don't know what the concentration of the salt is. As a matter of fact, what they say in here, this ammeter has a reading of 448 milliamps. So the current that is traveling in here through the circuit is 484. So it comes in here. This is fully charged, by the way, charged. So there is a current that comes in here, goes through this resistor, and then at the end comes back to the battery. And that current is 484 amps, milliamps, I'm sorry. So that is a current I. So we know what that is. That is given to us. So what they want us to do is first, so the ammeter registers a current of 484 milliamps. What is the salinity of the salt water solution? So in this case, this is what we need to do. We're going to use Ohm's law. And again, we're going to do points 1, point 2, which is the same point in here too, by the way. Point 3, which is the same point in here. Ammeters have negligible resistance, so this is the entire point 3. It's the same point. So this has no resistance, has nothing. So I say the voltage drop between 1 and 3 is the same voltage drop between 1 and 2, either way you take it, plus the voltage drop between 2 and 3, okay, because 3 is all over in here. So, and that gives me epsilon at the end is going to be Ri plus the resistance for the water. I need to call it different R than that one. So I'm going to call it Rw for water, okay? Rw for water times the current. Alternatively, if I go through the capacitor, is going to be Ri plus the Q over C. The Q on the water, Q on the second set. So I have two options, either here or here. But both of them, you need to add this voltage drop in them. So at the end, for this part of the problem, we already have the current I. We know what R is. We know what epsilon is. So technically, I can find Rw equal to epsilon minus Ri divided by the current I. Since we're given that, we should be able to find everything in this problem. But Rw, we need to calculate it as S naught over S times the length over area. So this becomes an equation for S. We can find the salinity because we know S naught, we know L, we know A, we know R, we know I, and we know epsilon. So we have everything. The only thing we don't have is salinity in here in terms of the standard value. So we should be able to calculate this one. That should be calculable, calculated. So that's your task, calculate, finish the calculation. Also, I can use the second equation now to find what Q is, because they didn't tell us what Q is, but we should be able to find what C is. C, I have all the ingredients for it. I'm not missing anything. So again, Q will be simply C, which is again epsilon R times epsilon naught times the length divided by the area. I'm sorry, times the area. Okay, they do it backward. You need to verify my algebra in here. Yeah. And this, of course, times epsilon minus Ri. Okay, I'm kind of a little bit in here. I really need to check on the capacitance in here. It was chapter 24. Yeah, I think it's correct. Here, C is A epsilon naught divided by D. That's the formula I'm using now. Okay? Epsilon times the area divided by the length. Okay? So that is correct. The length is the width in this case, okay? It's the separation between the two plates. So now we should be able to calculate this one. This is L. This is 3 centimeters. This is pi r squared, where r is equal to 5 centimeter. This is epsilon r, which is 80.4. This is epsilon naught something times 10 to the negative 12. Man, I have so many epsilons. This is the 10 volt. This is 15. And this is 0.484 amps because it's 484 milliamps. So this gives me that charge. Okay, so let's see what they asked. Okay, first of all, what is the salinity? So the salinity, you have to solve this equation for it. Okay, you have all the ingredients. This is 10, this is 15, this is 0.484, this is 0.484, this is 6.3 or something like that. What was it? Yeah, 6.3 ppt. And this is length, which is again 3 centimeters. That's the separation between the plates again, or the length of the wire, because this is a conductor now, so it's the length of the wire. And the area is still pi r squared, where r is still equal to 5 centimeters. So we should be able to get C from this equation. So I'm hoping that you guys will finish the calculation. B, the left cylinder acts as a capacitor. Use equation 24.19, which is what I used for its capacitance, most likely. If not, then please correct it. How much charge is present on its upper plates? Okay, so they tell you how much Q, and this is the Q. Again, finish this calculation for the second part. Okay. For what salinity level would the 15 ohm resistor dissipate half the power supplied by the battery? Now here is the deal. We want the power dissipated in here to be equal to the power in here to be equal to be half of the power that is dissipated by the battery. So that is basically the equation that we have to solve. In other words, since the current is the same, so we need the two resistances really to be the same. That's all we're saying. So this resistance needs to be 15 ohms if we are going to dissipate the same amount of power. No matter what current is, it has to be the same. Because if this one is delivering so many watts, half of it is in here. That means the voltage across it times the current, or Ri squared, need to be equal to this Ri squared. Cancel the I, doesn't matter, even if it doesn't stick to the same value, and it will change because this R now has changed, then they will be equal. So in this case, the salinity must be equal so that R is equal to RW, and R is 15 ohms, and then we have this one S naught over S times L over A. So again, you're going to solve for this equation for S. So this is going to give you S equal to some number in here, which is S naught over 15 times L, which is 3 centimeter, converted properly to meters, divided by pi r squared, where R is actually 5 centimeters, converted properly to meters, and you're in business, okay? So that gives you a concentration of salt in order to consume half the power in one or the other. The nice thing about this problem is that we can use actually electricity to find the concentration of salt in fluids. And that's actually very important. Okay, that's actually very nice. Does this problem make sense to you guys?
Yeah, it makes sense.
Very good. So please make sure
Yes.
you guys do all. Okay, very good. Make sure that you guys do these problems, okay? I don't know if I mentioned problem 59 or not, but it's similar to a problem that we do in Physics 4C from chapter 17, and it's problem 113. So if you really, from chapter 17, that is, I know some of you are not sitting in that class, but we did this problem extensively in PH4C. this semester actually, not too long ago, about a week ago only. Okay, so basically what you have in here, I don't know how the applications for this one really goes, but it's most likely probably for a some sort of a welding issue or something like that. And you have two different areas in here. So in this case, you have a length R1 radius. I'm sorry, we use lower cases R's for in here, not to confuse them with the resistors, and R2 in this case. And of course, in this case, the resistance will be dependent on how far you are in this case. So if we start counting from this point y equal to 0, and this is point y, the area, which is pi, this r squared, is going to change basically with from R2 to R1 or vice versa. Did I use the same symbols? Yeah, they call it R2 and R1. And the height in here also is given h. So as you go from y equal to 0 all the way to h, the area changes from pi R2 squared to pi R1 squared, okay? And you want to find the resistance. That's basically, which is rho times L over A. Except now you can't really find it, so you have to find it for this element in here only, where you neglect the change in the area for a small amount dy, the height dy, and you find that in this case, dr will be simply equal to rho times dy over A, where A is equal to this pi r squared. Now you need to find the relationship between r and y, which is simply going to be a linear equation in here. We spent a lot of time in that problem trying to find that relationship. Unnecessarily, it's a lot easier if we just solve a linear equation with coordinates in here. For y equal to 0, the radius is r2, so 0 r2. That's one point. The other point is when the height is actually y, the radius is r1. So now you have 2 points on a coordinate system. You can find how r depends on this is r, this is y. You can use that to find the slope, and you can find the y-intercept. The reason why you need that is because you need to carry this integration. You have a pi r squared. You need to sum from r2 all the way to r1. So r, the resistance, will simply be equal to rho times the integral of dy, varying from 0 to h, of this pi times this number a plus by squared. Well, you need to find this a and b from this thing. Once you do that, you have found the resistance, and now if you have an issue with the welding, for example, where that looks like this shape, so you can find what the actual resistance is, how much heat, how much losses of energy is in there, okay? This is basically in design. In that problem, in chapter 17 from problem 113 from Physics 4C, it has to do with the plugging devices, because on one side, so this side must be sitting on some voltage, the other one on some voltage, so the current must be flowing from one side to the other. In that case, you have actually temperature on one side and temperature on the other side, and you have heat being escaping through the, so think of it as a plug in that problem, and you have a plug that has this weird shape between, for example, an inside sitting at a different temperature than the outside, so that is how heat is flowing. So again, this is stuff, the idea is identical, so if you guys are into issues with it, please let me know. And I actually can give you the link for the video that we did for that class, and you can actually watch that one. It's about 20-minute long video where I solve the problem with 2 or 3 different ways, basically, on how to get to the same answer. Okay, so this is chapter 25. We really don't do a lot of problems because we're counting to do a lot of problems on chapter 26, actually. So that is how we're thinking, at least the way I'm thinking about this problem. So we're going to get into the ideas from chapter 26. So we're going to start it today. We actually started it a little bit the other side when we did the resistors in parallel, resistors in series. The reason why I had to do them then is because they are actually an issue in the lab that we're going to have this afternoon. So we have a lab, and hopefully you guys will be there to discuss all of these issues. The session for the lab is very short because you will see that it's actually does not require a lot of explaining, but there's a lot of work, as you have probably seen so far, okay? So let's get into this chapter 26. As I said, we started it a little bit, so let me share the screen. and it's chapter 26. Again, where did I put the pen here? So basically, here is a point. We have already discussed some components already, and we have quite a few things to do with circuits. We have introduced the resistor in this chapter, chapter 25, that is. We also discovered capacitor from before. We also discovered battery, which is just acts as a, so this is a capacitance, this is a battery, which is usually represented by its electromotive force. I also introduced a switch, which is necessary really, and you will see it actually in this chapter, needed to do some calculation on how to charge capacitor, because we did some problems in chapter 25, but we really didn't get into the details on how to charge a capacitor. So one of the items of this chapter is actually charging and discharging a capacitor, which is a lab on its own. So that is something that we're going to explore in here. So we have quite a few things in here. Here is what we need to solve all of these problems. And you will see that these problems have a common theme in them, and they become really an algebraic problems and sometimes very long and tedious algebra. What requires from you in this kind of problems is the focus, that's all. You need to be fully focused, okay? Once you solve them, it makes perfect sense for you and you'll be very, very happy with them. So we have rules for that. We have rules for that. We have 2 rules for that on how to handle circuits. And you need to remember these rules. This is actually the item of discussion today that I need you to think and put these rules in your own words, okay? Put rules in your own words. I'm going to explain what these 2 rules are. First of all, they have an owner. Mr. Kirchhoff is the one who came up with this one. Kirchhoff. That's how you spell his name, okay? And they're called in the scientific community as Kirchhoff's rules. Some people actually call them as KCL. That's how they refer to them. So if you hear somebody talking about KCLs, what they're telling you is Kirchhoff's circuit laws. They really don't really rise to the level of a law. That's why I'm very careful, and a lot of people actually, they refrain from using the word law for them because they are really not laws by themselves. They are actually derived from 2 very important laws. So there are 2 of them, first of all, okay? And they're rules more than a law. They're practical rules on how to solve problems in electricity. So what are they? The first one, so there are 2 of them, as I mentioned before. So there is 1 and there is 2. So the first rule is about a junction rule. That's what they call it. It's a junction rule. The second one is actually a loop rule. Okay. So what is a junction and what is a loop in circuits? Junction is when you have more than 2 branches meeting at the same point. Okay, and we have already seen that actually. We have, let me go back into here. This is actually a junction because I have more than 2 branches meeting in here. Actually, I have 3 in there. Same thing, this is a junction, this is junction, this is junction, this is junction. This is not a junction because it's only 2 branches in there. So it has to be more than 2, actually, 3 or more to qualify as a junction, at least of significant importance. So a junction when you have more than 2 branches. So in this case, I have 3. I could potentially have 4 or 5 or any number you like. Okay, we're gonna stick to only 5. Okay. So the branches could carry current that is coming, current that is coming to it, or leaving from it. Coming to it, or again leaving. For example, these 2 are leaving. Okay. I am going to choose the following. You don't have to stick with my convention. This is completely random. It's up to you. Whatever you decide on a given problem, it's irrelevant, this choice. I'm going to say when it's coming, it's positive because I'm thinking that it's bringing charges to the junction. So this is positive because it's bringing stuff to the junction. This must be negative then because it's taking it away from it. This is still bringing stuff, so it must be positive. This one, I'm thinking it's negative because it's taking stuff from it. This one also is negative in here. The junction rule says the following. The sum, the algebraic sum, I have to be very careful in here because you need signs. The algebraic sum of all the currents from all the branches is 0. Some are positive, some are negative. When you add them up, they will give you 0. Why? Let's say, for example, 10 coulomb came in, which is, let's say, for example, this brought 7 coulombs with it. This brought 3 coulombs for it, for a total of 7 coulombs that came into that junction. So 10 coulombs also must leave in the same time. There is no time for charges to hang around anywhere. They cannot accumulate in a given point. Why? Because of the conservation of charge. So this is really conservation of charge law. So that's why this law works. I mean, this rule works. So if I figure out that 1 coulomb somehow ended up going this way, and another 3 coulombs ended up going this way, so this is negative, then I know for a fact that 6 coulombs also went through this way. Because if I add 6 plus 3 plus 1, this is the outgoing, and this is the incoming 10. 10 plus negative 10 is 0. Okay? I can put it actually in English too. The sum of all incoming charges or currents, I should say, because that's what currents are. They're bringing charges, that's all. The sum of all incoming currents is equal to that of all outgoing ones. Okay, you don't have to have them divided equally, by the way, okay? You could, depending on the junction, what's happening in it, depending on that branch, what's going on in it, that's all. So a junction, so this is the junction, what I mean by it, but these are branches, okay? It's like a tree, basically. At some point, you have the tree branching out, okay? And each time there is a branching, in that case, there is a conservation of charge, okay? So that is the rule number 1, KCL number 1. Rule number 2, which is the loop rule, has to do with something else. And we've dealt with both of these rules so far. I mean, we didn't call them by name, but they are. So in a loop, I'm going to take just one loop, okay? I have a device in it. It could be a capacitor, it could be a resistor, it could be anything else. It doesn't matter. Or a battery or anything like that. Okay. And I've been doing that too, actually. I've been labeling things, okay? Well, for the loop rule, you need to do the following. First of all, choose a starting point, which must be your ending point. That's the key. So where do you start? Typically, you don't have to, again, you don't have to go with my convention. This is completely random. It's up to you. Where you start, you start. Nobody is going to tell you where to start, okay? Typically, you start immediately on the negative side of the battery. You start on the cathode. From there, you start counting, okay? And then you start counting the voltage. So if this were a battery, for example, and if this is me doing this problem, this is what I do. I start counting from here. This is my starting point. It's going to be my ending point. So I'm going to come back to it. So that's choice number one. Choice number two, you have to choose direction. Are you going clockwise, like the clock does, or are you going counterclockwise? It's up to you completely. There is no rule about it, which one to do. Same thing with the convention here for the signs in here. Which one you're going to call positive and which one you're going to call negative, it's up to you. There is only one restriction of this infinite choices, basically, is once you make your choice, you stick to it. That's the only problem. Once you decide on a starting point in here and a direction, you cannot change your mind in the middle. You have to continue through it, okay? So if I'm going to go clockwise, this is what I do, though, personally, and I think it's a good advice too, is to follow the current as much as you can. Sometimes you cannot really, you have no choice. You're going to go against the current, but that's basically, you have to work out that issue, basically, when you encounter it. We're going to talk about that, okay? And if you follow the current, you should be fine. So it could be clockwise, could be counterclockwise, but you have to stick to that one. You don't change it in the middle. You don't say, oops, the current now has changed direction, therefore I'm going to change it to go, I was going clockwise, now I'm going to go counterclockwise. No way. If you want this direction, you have to come back to the same starting point, okay, in that same direction. So now we have a starting point. I'm going to go clockwise. So the minute I hit a device, battery, resistor, capacitor, doesn't matter which, I'm going to start labeling, because this entire region actually the same point. That point that I represented anywhere in here is the same point. This one is going to be point 2, which is the entire thing is the same point 2. This one is going to be point 3, because I jumped over a device in here. So this entire region is 3. This is going to be point 4. When I come back in this scenario, I'm back to 1. So I'm going to start counting the heights now in terms of voltage. This is what I'm going to say. V1 minus V1 must be 0. This makes sense to anybody. I mean, if nobody has heard of Kirchhoff's rules or electricity, or has taken physics 4B or physics 4C or any physics at all, physics 4A or anything at all. If you give them this expression, well, that's what is that? I mean, that's obvious, isn't it? You throw in any number in there, it makes sense. That is exactly what Kirchhoff's rule is saying. This one is saying that delta V is 0. If your starting point is your ending point. This has actually a lot deeper meaning than that, and I will tell you what that is. So basically, with this expression, I'm going to write it as V1 minus V2 plus V2 minus V3 plus V3 minus V4 plus, I mean, I just stuck to 4 stuff in here. I could have a million of them. Plus, at some point, something minus V something, fill in the blank, plus that V something minus V1 is 0. That's basically what we're saying in here. In other words, the voltage drop in here is this added to this voltage drop, added to this voltage drop, added to this voltage drop is going to be at the end no drop at all. Okay, it's like, for example, I live on the, let's say, for example, I live on the 3rd floor. Okay, and today I decided to take the elevator and go to the 7th floor. From the 4th floor to the 7th floor, that's 3 floors basically up. Okay, then I decided to go to the 8th floor, 1 more floor up. Then from the 8th floor, I went all the way to the ground. Okay, so I went 8 floors down. Then I went back to my 3rd floor. I gained 3 floors. So how many floors at the end? Since I started from the 3rd floor and came back to the 3rd floor, where am I at? Where is, how many floors did I gain or lose in the same process? Nothing, because my starting point is my ending point. The only caveat is, in this case, in the case of the floors, what I'm really counting, I'm counting the potential energy, the gravitational potential energy. Because if I multiply that by mg, that is actually the potential energy for gravity. So how much gravity did I gain if my starting height is my ending height? Is nothing. So that is a conservation of energy. And this is exactly the same thing, with the exception that if I multiply this E by V, if I multiply this V by E, where E is the charge for the electron, or Q is the charge in general, if I multiply this by Q, what I'm doing actually is I'm counting the potential energy, but not that of the gravity, but rather of the electrical field, the electrical energy. So what I'm actually counting in this expression is actually the the equivalent of the gravitational field. The gravitational field in there has to do with G times Y. In this case is actually the gravitational, the electrical potential energy. So in this case, this loop actually has to do with the conservation of energy. Conservation of energy. And that is in a nutshell what we're doing with these things, okay? So these are Kirchhoff's rules. Obviously, they may not make a lot of sense for you right now, unless you, and they probably don't have a lot of appreciation for them because they sound obvious, but they will save the day when you have a very complicated circuit that has a bunch of loops in it and a bunch of branches, junctions in it, and you will be at loss. Basically, where am I going to start this problem? How am I going to start it at all? Well, in this case, identify the loops that you're going to be working with and find the junctions that connect them and write the equations there and there, okay? Obviously, at some point, you don't know which direction of the field, just take in direction and then follow it. Once you follow it, you're in good business, you're in good shape. Here is the deal though. If I have a resistor and the current, I chose it to go this way. So this is where the voltage drop is. And since this is actually keeping tab of the voltage drops, not the voltage rise, how the voltage is dropping from point to point to point to point to point. So basically, I'm seeing how much did I drop in height. So the fact that I went from the third floor to the 7th floor, I did not. Yes, I gained 3 floors, but actually I dropped a -3, which means I gained 3. Okay, I dropped with -3. That's the only thing. So when you rise, it's a negative. That's the only thing, because this expression is actually keeping tab of the drop, because actually when you drop, it's going to be, in this case, positive. When you rise, it's going to be negative. That's all. I mean, if you keep tab of the rise, that's fine. So everything, all the signs will change. So all you have to do is multiply the 0 by -1. It's going to be the same thing. So in this case, we're keeping really tab of the voltage. So this voltage must be high compared to this point, low, because the current is flowing this way. The current is dropping from a high voltage to a low voltage. So if I calculate Ohm's law, this voltage difference, which is V. So V in this case is going to be the V at the high point minus the V at the low point. That is what V is. That is what Ri is in this case. If I encounter the current in the opposite direction, if I'm drawing this thing and I'm coming from the low to the high somehow, because I drew the current going this way, then in this case, I have to write it minus Ri. I cannot write it plus Ri because I'm rising. And I'm keeping tab of the drop, not the rise. Since I'm rising now, this is a negative drop, which means I'm rising. That is the only thing that you have to keep tab of. Now, on a capacitor and a battery, if I see a positive to a negative, this is a capacitor, this is a battery. Again, this is typically how the current goes in here. Doesn't matter. This is positive, this is negative, even if it's open. There is no current flowing through it. This is high. This is low. This is high. This is low. Now, if I am going like this in this direction, then it's Q over C. Period. That is the voltage drop. If I hit the capacitor from the negative end, that is actually a rise. So it's a negative drop. So if I happen to go in my loop and my choice and I ended up somehow in the opposite direction of Q over C, that means I'm rising in potential, not dropping. So I have to write it minus Q over C, because Q over C counts the drop, does not count the rise. Same thing, the EMF in here, if I'm hitting it this way, if I'm going in this direction, it's actually negative epsilon because I'm rising if I hit it this way. I'm having it a negative epsilon. If I come through from the positive to the negative, that's it. It's negative. It's positive, I'm sorry. If I hit it in the opposite direction, that means I'm positive. So this is in a nutshell what we have to keep up. Down the road, we're going to discover other devices and we have to handle their voltage drops and see what's going on with them and so on and so forth. Okay? Make sense? I know I spent a lot of time on this KCL rules or Kirchhoff's rules, but I'm hoping that you guys have them clarified because we need them. We need them a lot for this chapter. How much time we have in here? We have a little less than 20, a little less than half an hour. Okay. We're gonna do at least something with these things in here when it comes to charging capacitor. We still have charging capacitor, discharging capacitor, which is part of this chapter. And then we're going to have a bunch of examples. Believe it or not, you will have a lot of examples before it's the settled, before the dust settles. Okay. So, and they become a lot clearer when you do more examples, by the way. So we're going to have charging a capacitor. Because a lot of these problems that we did from chapter 25 really didn't tell us on how the mechanism was. That somehow now the capacitors are fully charged. That we reached the point of saturation, basically, where you cannot put no more charge on the capacitor. Because I tell you, wait a long time for them to charge. How long is long? Should we wait for 10 minutes, maybe 5 minutes, half an hour, 3 years, maybe? That is the question. So we need to know the time scale onto how much we need to wait. The other interesting question, how much charge do you think we're going to have for a specific capacitor? Well, that depends on the battery that provides the power, really. So let's do that. So here is the scenario for charging a capacitor. This is, by the way, another lab, okay? So here is, I mean, we're going to do this lab later on. So we have a power source. We have a switch that can be turned on and off. Next to the switch, we have a resistor, R. And after that comes a capacitor. Simple loop, only one thing in this loop. I mean, only one loop, I'm sorry. All the devices that we have seen are in here, in this loop, okay? Here is the goal. At t equal to 0, namely before we threw the switch into a position, there was no charge in here. So Q was equal to 0 at t equal to 0. So that is the time when I decide to throw the switch in the on position. There is an EMF in here from the battery. Doesn't matter how many volts it has. And now the current starts to flow in the circuits. So if I wait any time later, okay, there is a current. So now it's t is more than 0, by the way, now, which means that this thing is close. So that means there is a current now that is trying to pile up charges on this side, Q on this side. Obviously, I have to drain charges from the other side. That's what the role of the capacitor is. Okay. By definition, the rate at which the rate at which charges are being piling up in this case, adding up, is going to be given by I dq over dt. This is a current, actually, how it's related to the charge. My goal is the following. I want to build this Q charge. I want, after all of this, is to build the charge Q, which I need to know how much it is first. And then I need to know how long does it take for it to charge, so that I can basically go on with my own life. You guys understand? So that we can do other things. We don't be just stuck in here charging capacitor for a long time. So we need to know that. So that is how the problem is set up itself. Now, there is another side to this story, and there's always another side to any story, is once it's fully charged, how can we get rid of that charge? So So the discharge of the capacitor also is another interesting issue that we need to explore down the road. Okay. So this is how the problem set up itself. So again, we're going to apply Kirchhoff's rules, that's all. Following my own advice, I'm going to choose my starting point here. I could have chosen at any point. But what I'm saying in here is I need to come back to this point after all the said and done. What I'm going to do is, because I see I have chosen the current in this direction, coming from the positive side of the battery, which is usually good advice to do. If this choice is not good, I will turn out to be negative. Okay, I will turn out to be negative, that's all. And this could be, even with this configuration, if I started with a big charge in the capacitor, then the capacitor will have more power to push through even the resistor, the battery, and will push the current in here and get rid of some of that charge. So that could be the case, but not probably for this scenario. Anyway, by the way, I did not probably say this in the lecture. Usually the negative side, which is called the anode, the cathode, sometimes is represented with a thicker line than the anode, than the positive side of the battery, just to make that distinction between the two. Anyway, so I'm going to choose this direction to be the direction I'm flowing in it, okay? The reason why I'm saying that is so that I don't have to run to that minus sign for the Ri. And as a matter of fact, in here too, this will be positive because I'm coming from positive side to the negative side. So this will be Q over C. I'm in good shape now. Here is a problem though. This point in here, I have to jump it in the opposite direction. I'm going from the negative to the positive. So that means I'm rising in potential. So if I do this calculation from point 1 to 2, this will be actually minus epsilon because I'm rising in potential. I'm not dropping. But from 2 to 3, I'm actually dropping in potential. I don't need to draw a point in here because once you close, it's only just a line. Okay? So this is the assumption. I'm assuming that somehow I close the circuit in here when it's turned on. So this line is just one line. Okay? So once in here, I drop from 2 to 3. So that's fine. It's going to be Ri. And from 3 to 4, which is back to 1 actually. So this is 1. Then I'm actually also dropping in voltage from positive to negative. So that's going to be fine. It's going to be Q over C. So we're in good shape. So we're going to write Kirchhoff's rule now for this circuit. The first point is we are rising in potential. So we are minus dropping because we're going from negative. So I probably have to write it more explicitly in here. So what I'm saying, V1 minus V1 is indeed V1 minus V2 plus V2 minus V3 plus V3 minus V1. This one is minus epsilon because this is actually a rise from V1 is less than V2 because V2 is a higher potential in here because it's on the positive side of the battery. So again, this is minus epsilon 2. Okay, because V2 minus V1 is epsilon, so V1 minus V2 is actually minus epsilon. V2 minus V3, which is this drop in potential, that is my Ri. And this is V3 minus V1, which is Q over C. So we're in business, and this is 0, by the way. That's Kirchhoff's rule. So what we're saying in here is that 0 must be equal to minus epsilon plus Ri plus Q over C. And we have a relationship between Q and I. I is actually the derivative of Q with respect to time. So what I'm going to do now is write this expression, move the negative epsilon to the other side, and I have R times di over dt, dq over dt, plus Q over C is equal to epsilon. So this is the equation that we ended up with. And it's actually a differential equation, okay? It's actually an integral. All we have to do is just find the antiderivative of this expression. So let's do that. Let's move this side to the negative side, to the other side, I'm sorry, and change its sign and divide by R at the end. So this is how it's going to look like. dq over dt is going to be equal to, the common denominator is C, by the way, and time is R when I divide by it, RC. And then I will be left with an epsilon in here times C, because when I find the common denominator, I have to multiply by C. So this is C epsilon minus Q. So this is the expression that I need to find a solution for it, which is an integral that I need to do. What I'm going to do is the following. I'm going to write this expression in a slightly different fashion, where I'm going to put a minus in here and change the signs in there, because then I can say dq over dt is equal to minus q minus c epsilon over rc. All I did in here is just change the signs, that's all. And it's important because I really need q by itself in here. I don't need this c epsilon. Even the c epsilon is not important for me. So what I'm saying in here is the following. D of q over q minus c epsilon is equal to minus dt over rc. We're going to make change of variable because this nonsense stuff in here is kind of an annoyance, this constants in here. Because if we're going to integrate, we really need to have a clean integral. So what I'm going to say in here is that I'm going to define q prime so that it's actually q minus c epsilon, which means that dq prime is the same as dq because c is constant and epsilon is constant, so this is a constant. So when I take the differential form of both sides, it's just the same thing. So this integral then becomes, this integral is easy because r and c are constant, so it's just the integral of dx, which is just x. Okay? So what I ended up with in this case is dq prime over q prime is equal to minus dt over rc. So on one side, I have the integral of dx. On the other side, I have the integral of dx over x. Do you guys know what the integral of dx over x is?
Isn't that just ln of x?
That should be. That's very good. Thank you. So this is ln of q prime is equal to minus just t over rc plus a constant. That's because I'm just interested in the basically the entire derivative. I mean, that's all. This is an indefinite integral. So again, if I exponentiate both sides, I'm going to find q prime. And q prime, remember, is just that thing there. It's q minus c epsilon. So I'll find q minus c epsilon being equal to an exponential of a constant, which is another constant. So whatever that number is going to just be another constant. Time is the exponential of this guy, which is minus t over rc. Okay? Move the c epsilon to the other side and we're in business. Or immediately, first of all, do the following. We know at t equal to 0, q was 0. In other words, q sub 0 is 0. Because there were no charge in the capacitor when we started this whole thing. So I'm going to sub in this expression by t equal to 0 and q is equal to 0. So this is 0 minus c epsilon equals to a constant times exponential of 0. Exponential of 0 is 1. So that means my constant is simply negative c epsilon. So this is the expression then that we get. This is, by the way, an example of the initial conditions. When you're solving equations of this type, you really need to come back to them, initial conditions. You only have one. And that helps you find that constant, those constants of integrations. So now we have q minus c epsilon is equal to minus c epsilon exponential of negative t over rc. And if I move negative to c epsilon to the other side and take it as a common factor, it's going to be positive. So q sub t now is equal to c epsilon times 1 minus exponential of minus t over rc. So this is how we charge a capacitor. This expression is of utmost importance because it helps us understand how we charge a capacitor. There is another expression that I really need, is that the cause of this charging of the capacitor, first of all, if I wait a long time, when t goes to infinity, q sub infinity, when t goes to infinity, is actually the ultimate charge q that I want. And this term goes to 0 at that time for t going to infinity, because exponential of negative infinity is 0, basically. It goes to 0. So in this case, I will have 1 times CE, and that is the charge. So this is the charge I'm going to end up at the end of the day when all the dust settles. When this charging is finished. Obviously, I'm saying it takes an infinite amount of time. So my hopes are dashed in terms of how long does it take me to go really and wait for this one to be fully charged. So I don't have a choice but to wait an infinite amount of time. So we'll see how big infinity in this case is. That's an interesting question. Now I need to find this current I. I is dq over dt. So I need to take the derivative of this expression to find what the current is. So I, which is actually current that also changes with time, should be just dq over dt, which is a derivative of a constant, which is 0, minus the derivative of the exponential. So minus this constant C epsilon times the derivative with respect to time of this exponential of minus t over RC. The minus and the minus cancel, and that's good. Because if this current turned out to be negative, I have a problem. Then how am I going to charge a capacitor if the current is actually flowing in the opposite direction? So we need actually current to be positive in this direction so that it stays positive. So the derivative of the exponential brings down the negative, and it also brings down 1 over RC. So it's going to be I sub t is going to be a positive number, which is very important, C epsilon divided by RC. Obviously, the C and the C cancel, times the exponential, of course, because the derivative of the exponential is an exponential too. So the current is positive, and it's equal to epsilon over R times exponential of minus T over RC. Here is what's going on then with the current. Initially, when I just throw the switch off, that is T equal to 0. The current is epsilon over R. So there is tremendous amount of current. And then with time going on, the exponential starts to become smaller and smaller and smaller. So the current will start to go less and less and less. So at the end, when this is fully charged, which is infinity, the current should be 0. Because the exponential of negative infinity is 0. That's what justified earlier what we were doing for chapter 25, in a sense, that when these guys are fully charged, they don't take any more charges. That they kill the current that is going through them. So it's like an open circuit, basically. That's all. So let's draw this graph, these functions. So this is t. This is q as a function of t. Initially, there was no charge. And at the end, the full charge is going to be C epsilon. Okay. So at the end, we're going to reach the saturation, which is C epsilon. So that's the limit. And it's going to grow exponentially like this. Okay. The current, on the other hand, drops from an initial value down to 0 exponentially also. So the current, I as a function of time, also drops from this value, epsilon over R. That's how much it is when t equal to 0, epsilon over R, down to 0 also. Because the capacitor now is getting more and more charges in it, and it's going to kill any current because it's fully charged now. Okay. Here is an interesting question, really, and it's important. Because should I really wait an infinite amount of time? How big should I wait? Because look at this current, for example. It drops, and it's characterized by this time, which is kind of called the time characteristic, tau, which is RC. Because if I wait a tau amount of time, if I wait an RC, the current after t equals to tau is simply going to be epsilon over R times 1 over E. Because again, e to the negative 1. Because when t is equal to RC, this just becomes 1 over E. So that means it drops by a factor of almost 3, a third of its value, just after waiting for 1 tau time. So this is called the characteristic time. Okay, for the RC circuits. This is, by the way, an RC circuit, okay? I forgot probably to mention this. This is an RC circuit. Okay, I know we still have about 5 minutes. So if I wait twice tau, this is going to be 1 over E squared. That means it's going to be almost 1/10 of its initial value of epsilon over R. If I wait 3 tau, it's almost 1 over, 30th, okay? And so on and so forth. So drop so much, actually. If I wait, let's say, for example, 1,000 times tau. If I wait 1,000 times tau, this drops by 1 over E to the power 100,000, which is practically zero, no more current flowing. That means all the charge is in there for all that time. So let's look into the problem that we just did, for example, and see how much RC was in it, okay? Let's take problem 70. In problem 70, you have a C, which was, one of them was 6 microfarads and the other one was 3 microfarads. It doesn't matter. So of the order of microfarad, even if it's a 10 microfarad, like the problem after that. So C, let's take the big number in here, was 6 microfarads, okay? And R in that problem was of the order of, we found it to be 22, the biggest one. So I didn't take the smallest one, which was like 2 ohms. So I'm going to take 22 ohms. That's what we found. So if I do the calculation in here, 6 times 2 is what, 12? 6 times 2 is 12 plus 1, that's 13. So tau is going to be 132 ohm times farad, that's second, but don't forget the micro. So this is how much time we're talking about, okay? So if I wait 1 second, 1 second is almost 100,000 this number, or 10,000 this number at least. So it's 1 over 10,000, which is 1 over e to the power 10,000. If you put it in a calculator, you're going to give you 0. Actually, as a matter of fact, let me see if it's going to give me a number. 1 over e to the power 1,000, 10,000. This is a very, very powerful. It has a long sig pix and it's giving me 0. So the current is practically 0 if you wait a second. And this one is practically E because this is 0 also. This is 0, it's 1 over that number, e to the power 10,000, and it's just CE. So all you have to do is wait a second. As a matter of fact, fraction second will do. So this business of waiting an infinite amount of time and infinity and things like that, that mathematicians basically work with all the time, and epsilon and things like that, they don't mean that really literally you have to wait for that time. All you have to do is just wait a fraction of a second and it's fully charged. Turn on the circuit, and before you probably grab your ammeter and your equipment, you already have it fully charged. Obviously, sometimes we want this discharge to happen at a different rate than what we want, or sometimes more or less, depending on the situations. And this is usually depending on the applications. For example, the flashlight that the cameraman uses for flash, that is actually uses a capacitor in there. During the discharge, you have that light that comes from there. And then you wait for it to charge again to do that. Okay, at least in the old days. Now it uses different technology. Anyway, this is in a nutshell the charging. We still have 1 minute and we have a lot of things to talk about. Here is what we need to talk about next time when we meet. 2 items before we hit the problems. First of all, the energy. Remember, it does not really matter until we talk about the energy. Here is the deal. We have an energy in the capacitor now that I can find. It's 1/2 of Q squared over C. And because we built a charge and we waited an infinite amount of time, we know what Q is. It's CE, C epsilon, C times the EMF. So now we know how much charge we're going to end up in the capacitor, which is 1/2 of this number squared, C squared divided by C, that's C, times the epsilon squared. So this is the energy that is now stored in the capacitor. Obviously, my question is, where did that energy come from? And the circuit, could it be coming from the resistor? Or could it be coming from the battery? Or could it be coming from the switch? It would be nice if it's coming from the switch, then we don't need anything at home. We don't need to pay the power company anything. We can just use the switches as sources of energy, but it's not. So that's going to be the last question in here of the day. Which one do you think is coming from? It's coming from the resistor or the battery?
The energy would come from the battery, wouldn't it? Because that's the only thing. That's the only. Yeah, it's the only thing providing any type of power current in the circuit. So it'd be nice, like you said, if the switch provided all that energy, you know. There's a what's it called? There's a term for it. Where you self-propelling energy, something like that, mechanism.
What do you mean? No, I don't forget the name for it. Yeah, I know what you're saying. Anyway, the point, that is the culprit. Okay, so here's the deal. Next time when we meet, we're going to see how much energy we drained from the battery. And you and I, we agree it must be at least this number, because if we find that we have less from that, so we have to go and dig some more, trying to find where we need the extra energy to account for this energy that is stored in the capacitor. Okay. If we end up with more, then we have to wonder, where did the rest of the difference of the energy went? It really doesn't matter until you have a full energetic analysis of your problem. Any circuit, any problem in physics, that is the most important thing. Because that's where the money comes in. That's where you have to pay for things. That's where you have to go to the gas station and pay for energy. I mean, it's all have fun and time and things like that with the car until you go back to the gas station and fill it up. That is really when it matters too. So the same thing in here. So we really have to know that we need to have as much energy, at least, if not more, coming from the capacitor, from the battery. And if that is fully accounted for, then we need to wonder about the difference, if there is any. If there is no difference, then we're in good shape. We're fine. Okay. So that is what we need to do. And then we have to do the second thing, which is discharging a capacitor. So those are the two things that we need to talk about. And then we're going to do problems from this chapter. Anyway, we have lab this afternoon. I'm hoping that more of you guys will show up in the lab, because albeit it's short, but it should cover all the stuff that is needed for you guys to do your lab. Okay. See you guys at 5 today. Okay. Let me stop the recording.
All right. See you at 5.
See you.